In this video, we'll examine the convergence of the power series that I'm calling g of x, whose terms are given by the summation in this expression. In the numerator, I have x plus 2 to the n. In the denominator, I have powers of 3 times 3n factorial. Let's write out a few of those terms. The first term, when n equal to 0, will be 1, because I have 3 to the 0. I'll have 3 times 0, so I'll have 0 factorial, which is defined to be 1. And I'll have x plus 2 to the 0 power, and that it will be 1 as well, so I'll see 1 in the first term. In the subsequent terms, I'll see increasingly high powers of x, so x plus 2, a linear term, x plus 2 squared, x plus 2 cubed. Then we'll see increasingly higher powers of 3, 3 squared, and 3 cubed. And then we're seeing multiples of 3, and then they're factorial, so 3 factorial, 6 factorial, 9 factorial, etc. What we're going to do next is look at where this series converges, and one value of x is obvious. It must converge at its center, which in this case is x equal to minus 2. If I take x to be minus 2, all of these terms here with x plus 2 will be 0, and I'll be left with the constant term only. So g of minus 2, my series at minus 2, will be equal to 1. The question becomes whether or not it converges for other values of x, and we're going to use the ratio test to check whether or not it converges, and in fact we'll be checking for absolute convergence by using the ratio test. We'll begin by identifying the nth term of the series, so here I'm calling it an, and I'm taking my typical term in the series. I'm going to look at the next term in the series, so I take an plus 1. Every power goes up by 1, the exponent goes up by 1. Notice when I take n plus 1, for n in this expression here, I'll actually have 3 times n plus 3. Be careful here evaluating 3 times n plus 1, but that will be tripled, so I'll see an extra 3 here in the factorial. The ratio test then considers the limit of the ratio of consecutive terms. Because these expressions involving x could potentially be negative, I need to take the absolute value. So we're going to look at an plus 1. That's the term in blue, and instead of dividing by an, I will multiply by its reciprocal, so I'll flip it over and multiply by that term, and then we'll take the absolute value of that and see what happens as n becomes large. There are some factors that are in common. I have 3 over n, or 3 to the n, over 3 to the n plus 1, and certainly there will be some canceling there. I have these two factors with factorials, so I'll keep them together. And then I have these two terms that have powers of x, and I'll keep them together. Notice these terms are all positive and so don't require the absolute value, but the terms involving x could potentially be negative, and I better keep the absolute value around those two factors. Now doing the canceling, I'll see 1/3 when I cancel here. In this expression, when I do the 3n plus 3 factorial, I first have 3n plus 3, 3n plus 2, 3n plus 1, and then the remaining factorial will be 3n factorial, which will cancel with the numerator as well. So there will be 3 factors left behind. And then I cancel the powers of x, and I'll have x plus 2 in absolute value. Must preserve the absolute value here, but not necessary in the remaining factors. Doing the canceling, I'll have some rational expression in n, 1 over 3 times these powers, or these factors that were left in the higher factorial, and then times x plus 2 in absolute value. As I let n go to infinity, this whole expression here, regardless of the value of x, will go to 0, driving the entire expression down towards 0. So as n goes to infinity, this limit of the ratio of consecutive terms will be 0. Because that number is less than 1, regardless of what the value of x is, the ratio test says that it converges for all x. Another way of saying this is that the radius of convergence is infinite, or that the interval of convergence is the entire real line minus infinity to infinity.